Okay, it's past 7:30, so let's get started. Welcome to System Software. I guess we've been here for 2 weeks, but it's the first time we're meeting face to face, so nice to see you all. Hello. Okay, so I hope everybody is mostly doing okay setting up all the tooling. I know it's a little tedious maybe for some of you, but if you're going to go into computing, it's really useful to know how to use computers and use tooling, computer tooling. So I know some of you are struggling, particularly with like Windows. So I don't have a Windows machine to try this stuff on, but I think I figured out what's going on, at least with some of the machines and some workarounds. So first of all, who has the tooling all set up? Wow. Who attempted to get all the tooling all set up? And who failed to get all this? Who's ready to admit it? Okay, so people are still struggling with setup. Who's using Windows and having trouble still? Okay, so one thing you can do is just use Windows Subsystem for Linux. Who has not heard of Windows Subsystem for Linux? Okay, so apparently you can just go to the Microsoft Store and download Ubuntu 18. So I sent out an announcement on web courses, right? Did you guys get this announcement? Yes? Yeah. Recent today? You can just download Ubuntu 18. Yeah, question? Previous versions of Windows? I don't know. Upgrade? Is it free to upgrade or not free? Then use Vagrant and use the Vagrant in the virtual machine. So you should be able to use VirtualBox even on older versions of Windows. And that Vagrant file I gave you and that virtual machine I gave you should just work. So if you're still struggling with it, ask in lab, come to office hours. A number of students came to office hours today. Who cannot come to any of the office hours? Okay, and if you didn't actually look at what the office hours are, then, oh well. So everybody can come to office hours, that's my assumption. Okay, any other questions? Yeah.
The second homework, how do we submit it? Do we submit it in GitHub or
No, you just submit it on web courses. Just cut and paste, put it on web courses.
Where do we do the assignment?
In your Vagrant virtual machine. Yeah.
And we're just supposed to type out to the thing that Vagrant prints out to when we run the homework assignment, right? Yeah, you just compile it and run it. And I'll go over an example of doing that near sometime in this lecture. So I'll go over it again. But you do need to have, at a minimum, you need to have Clang, this compiler, which is very similar to GCC, but has some differences that we're going to take advantage of in this course. As long as you have Clang version 6, that's the version we're using to grade. If you're using the Vagrant virtual machine, then you don't have to worry about it. It's all set up for you, as long as you can struggle through getting those tools set up. But I do want to point out, one reason that I'm doing this is because, as I mentioned in the very first lecture, I think a lot of, who wants to be a software developer? Okay, a lot of you. Who's going to stay in computing? Okay, yeah, some adamant, if not explicit support for computing. So this is like the bread and butter of computing. Unless you're doing algorithms or math, you have to use computing tools. And Vagrant, VirtualBox, or VMware and Docker are other options. GitHub, GitLab, Git, SVN, Subversion, Mercurial. These are all standard state-of-the-art tools that I'm sure 99% of you are going to encounter in whatever computing and every endeavor you do. So being able to go into a job and just quickly get set up with these tools and not spend a few weeks. They don't want to pay you to spend a few weeks to get your tooling set up. They want you to just hit the ground running and start working. So I think this is a little bit of a good exercise, and it's easy, right? This is not conceptually challenging. It's sitting down at a computer and getting this stuff to work. And for some of you, I know it might still be kind of new to computing and computer science, so it might be a bit of a struggle. But come to office hours. We're here to help get all this set up. And once you have it set up, it should be smooth sailing with the virtual machine. There shouldn't be any grading issues. Any other issues on getting set up?
If you're still stuck, please come to office hours. Masood has office hours tomorrow. I have office hours Thursday. So just come to office hours and let's get this set up so you can start doing the project. The point of homework 2 is to make sure that you have the setup. That's really what homework 2 was. There's nothing tricky about it. It's literally just taking a file, compiling it, and running it. Something that all of you have done in some capacity, but maybe not on this exact tooling setup. Okay, so without further ado, let me get into the lectures. I do want to say another thing. So I think I'm just going to put all of the lectures on YouTube. So I'm recording all of them with this little nifty plugin in Chromebook. We'll see how that works. I am using a Chromebook. If you have any questions about that, ask me after class. That might be an interesting choice for some of you. But let's just get started. So in this class, I want to go over what compilers are on the internals of a compiler, how a compiler, the actual infrastructure is built. And for our first project, hopefully some of you have started looking at Project Zero. You're actually going to be writing a complete working compiler for your first project. But it's very, very, very simple. And I promise you it's going to be very easy. Pretty easy. But you're going to be writing a complete compiler. And then over the course of the semester, we're going to be building on this compiler and adding new features and new language constructs to this compiler. So this is like, did anybody buy the Dragon book? The compilers, Aho, SETI, Omen? Who bought the Dragon book? I didn't hear that. Who acquired the Dragon book? Let's put it that way. Okay, so the Dragon book is, I recommend it. It's a good resource, or borrow it from a friend. From a friend. It's very formal and kind of mathematical, but it gives very rigorous definitions of everything we're going to talk about in this class. So you can probably get by with the lectures and the notes, but it might be good, especially for some of the homeworks, for some of the more formal concepts. It's good to have the Dragon book. Actually, I'm going to use the laser pointer here so everyone can see. Oops. Okay, so this whole thing here, this is at least the Dragon book's diagram of a complete compiler. Now we're going to be doing something much simpler to this, but I just want to walk you through the kind of internals of all that magic that's happening when you just type GCC and you compile and run your program. There's actually a huge amount of computer science and engineering that went into this just to take your piece of code and turn it into machine code. So in case you're not aware, that C program you write, there is no physical machine that I know of that is actually running that program. That C is like a lie. There is no C language in the real world. The reason the C language runs is because the compiler, just like a language interpreter, translates that language to machine code. So I think all of you have taken computer architecture at some level and played a little bit with MIPS or some other assembly language. That's the language that the machine can actually interpret and run. But these high-level languages like Python, Scala, C++, C, these are not being interpreted by the hardware. Instead, they're being translated by the compiler in order to be run on your hardware. Is my mic cutting out? Is it okay? Okay. Or it's being interpreted by a software or a virtual machine. But in this class, we're going to be talking about compilers. So the main phases of a compiler are lexical analysis, and this is basically turning that stream of characters, because every text file is just a stream of characters, turning that text file into words. So instead of this, perhaps a little hard to see, instead of this little assignment statement here, we've got a list of the words of this language. There's an identifier, there's an equal sign. And then, just like you probably learned in elementary school, this is turned into a syntax tree, basically sentence diagramming. Does anybody remember doing sentence diagramming? Who did sentence diagramming? Wow, nobody? No comment. So sentence diagramming, it's just this is a noun phrase, this is a verb phrase, this is subject object. That's what your compiler does automatically, internally. Ooh, it turned on the night mode. Let's get rid of that. I don't want you guys falling asleep yet. So it's basically doing sentence diagramming. The next step, it's doing semantic analysis. We'll talk about that a little bit more. It's basically saying this symbol is an integer versus this symbol is a function, or this symbol is a Boolean. And then it's generating intermediate code. So modern compilers, instead of immediately spitting out machine code, they spit out this kind of abstract form of machine code. And that's what our LLVM intermediate representation is. It's a industry standard intermediate representation for writing compilers. And then behind this, after that phase, after we have that intermediate code, there's a bunch of algorithms that make the code more efficient, the optimization. And this is avoiding memory accesses and using registers. As you know from architecture, register computation is much faster than going out to memory. So compilers will automatically make these optimizations to make your code either run faster or be smaller binaries. And then finally, the code generator spits out our machine code. So that's the kind of what an industrial strength compiler does. We're going to be doing something much simpler. So the kind of overall schematic of what your compiler program is going to do, and it's going to be called Simple C, as we talked about. You got to use a makefile, like we talked about in the last lecture. Use that makefile, and whatever C files you have will be turned into the Simple C program. And your Simple C program will just read one character at a time from your source file. These source files are called Simple C source files. And it's going to spit out this LLVM intermediate representation that we looked at a little bit in the last lecture. So that's the kind of high-level schematic of what your compiler is going to do. And to process the input file, we're going to use some standard C library function. So has anybody actually used fgetC before? Nobody's? Okay, not much. So this might be a little bit new to you. But as long as you can open, you know how to open a file, right? Use an open. You say open. Who can open a file? Open a file and say, okay, good. So they're just like printf or fscanf. Printf is writing to a file. fscanf is reading from a file. fgetC is just getting a single character from a file. And so that's how we're going to be able to read this source file one character at a time. Because remember, the machine does not know anything about the C language. It's your compiler that gives meaning to these symbols that are the input. And effectively, you're just going to have an endless loop inside of your compiler that's just going to be reading one character at a time until we see end of file. So EOF is a C standard macro. That means you've seen the end of the file. So once fgetC returns EOF, you're at the end of the file. So you've either seen a real source file or there's some error. And then we're going to use a couple of these helper functions to determine what kind of character this is. And I'll get into that a little bit more. So to emit the output file, emit our LLVM intermediate representation, all you have to use is printf. So everybody knows how to use printf. And have you actually used format strings like %d? Who's used format strings before? Okay, so everybody's familiar with this. So all the compiler really does at its base is just printing out text. It's just printing out another program. But the other program that we're printing out is not in C, or it's not in some human language. It's machine code language. And so at the end of this, I'll give a little tutorial on what the LLVM IR instructions look like. But effectively here, this is a template for doing an addition. So you can see here's the add instruction in the LLVM intermediate representation. And we have placeholders for the variables that we're using. This actually should be S string, not D, sorry. But you have placeholders for the variable names that you're going to use for the operands for the addition and where you're going to save the operands. So LLVM looks a little bit like C. So it's basically just taking something that looks like C and translating it into another language that also kind of looks like C. So as I mentioned, each project is a complete working compiler that takes simple C and turns it into LLVM. But each of the projects adds a new language construct. So we're going to start with very, very simple arithmetic operations, just one statement that says print out one arithmetic operation, one addition, one subtraction. And then we're going to build this up to allow full math-like arithmetic expressions that you're used to, with parentheses and order of operations. Then we're going to add variables to this. So we're going to see how variables are actually implemented at the low-level architectural level. Then we'll add control flow, if statements, while loops. And then finally, we'll add functions. Functions are a little bit more complicated in its syntax and implementation, but we'll see at the machine level how functions actually work. And so for each of these projects, we'll look at the target language. So the target language is the output of the compiler. We'll look, and that's going to be LLVM intermediate representation. So I'll give you all you need to know about the target language for that project. We'll go over the source language, all you need to know about the simple C language. And I'll sprinkle in a bunch of relevant compiler theory, which I think will be interesting and useful beyond this course. So for instance, regular expressions. Who's used regular expressions before? So, okay, so maybe a third of you. They're extremely useful. Once you learn them, you can use them in all your IDEs, you can use them for search. And so we'll go over some of the actual theory and formal theory behind that. Okay, so let me start by going over Project Zero. So there's going to be a couple of representations here that are probably a little unfamiliar to you. And as the course goes on, we'll go into more detail about what this representation means. But this, I don't have a pointer. This section here is called the grammar specification. And just without going into details about how grammars work, intuitively you can see that what this line is saying is that a statement in our language is comprised of a print word, an expression, followed by a semicolon. So intuitively you can kind of grasp, like in C, this is what you're writing in C when you do a print statement. You write print, you write some string, you write some expressions, you have a semicolon at the end. So this grammar is a general way to describe every possible input program. And if you were to look at the grammar for C, C is a much more vast language. Its grammar is hundreds of lines long, but it's a comprehensive description of the syntax of the entire language. So just like in English, we have syntax descriptions that describe, a noun placement, subject, verb, object, order. That's the syntax of the language. So without even realizing it, when you program in C, you're obeying certain syntactic constructs. And that's why your compiler complains to you if you miss a semicolon or put something out of place. It's this syntactic analysis that is interpreting that part of C. So for this first project, we don't really have to go into too much detail about what the syntax looks like. We can basically do it by example. So there's only two shapes of statements for our language. We have something where we have a print statement followed by a number, followed by an operator, followed by another number, and then a semicolon. And that's one of the types of statements that we have. So I think I have more examples here. Oops, that's slow. So this grammar specification, as I said, provides the syntax. So it formally describes statements like a program is a list of 0 or more statements. That's kind of obvious, right? But remember, this is a machine. The machine does not understand language. Or something like a print statement contains the print keyword followed by an expression followed by a semicolon. So that formal, formal representation that you saw is really just a mechanical way of describing English language descriptions of our programming language like this. And then we're going to talk about this more in today's lecture and next lecture. If we have time today, we'll talk about it. The lexical specification defines what the symbols of the language are. These are like the words of the language, the nouns or the articles, the indivisible atoms of your language. So for instance, an identifier in our language can be described as a starting letter followed by 0 or more letters or digits. So in C, you can't start an identifier with a number because the compiler thinks that's you're writing a number. You can't start it with a digit. You can't start it with a digit because the compiler thinks you're telling it a number. So the identifier has to start with an alphabetic character, but then it can be followed by 0 or more digits or alphabetic characters or underscores in C. Or the print keyword is just recognized by matching, print, the literal print string. So there are mechanical ways to define these aspects of the language that we're going to go into in more detail in this class. And for Project Zero, there are really only 2 patterns of statements that you can already kind of start recognizing these with code without really understanding all of the details of how formal syntax works. And there are 2 main statements. One is just the print keyword followed by a single number, followed by a semicolon. And the other type of statement is just a print keyword followed by a number, followed by an operator, followed by another number, followed by a semicolon. So does anybody have questions about these patterns of statements? Is there anything that's uncertain about them? Or yeah?
So it doesn't necessarily recognize, say, -5 as a number -5. It more so recognizes 5 times -1.
Actually, here it recognizes the symbol for minus followed by the symbol for 5. And so -5, both of those characters together are considered a single number. And as an extension to this, all of these examples are single-digit numbers, but you could, of course, have 29 or 307. And so in order to interpret something as a number, we have to actually read through each digit of that number in order to interpret it as a number. And as we'll see in a little bit, what looks like a number in text is not actually a number in the machine. Some other caveats here. So notice that we've got the minus sign here twice. Now this is the same character, but they have different meanings to the compiler. So just like your classmate asked, this minus, how do we interpret this minus? Well, this means it's a -5. It means we want to have a negative number. This minus means do a subtraction operation. So that may seem like a minor distinction, but once we actually start compiling this to LLVM or compiling it to machine code, that distinction really matters because the minus sign means do an assembly language subtraction, whereas the minus sign before the 5 means just represent this number using 2's complement with negation. Did you all study 2's complement? And yeah, so this is saying use our 2's complement representation to represent this as a negative number, but the second minus means use the architecture's subtraction operation. So this gets a little tricky because this is the exact same symbol in terms of the source code. So our compiler has to be aware of the structure of this language in order to interpret those symbols correctly. So yeah, something to think about is how can your compiler tell the difference between these two minus signs? So any takers, any ideas about how a compiler may know that these two minus signs mean different things? Yeah. Spaces. Okay, so you might say that there's no space between -5 and 7. Okay, that's one way to look at it. But remember, in C, you could write 5 minus 7 without spaces. That's also possible. So you in the hat.
You use if statements to distinguish.
You could use if statements, but okay, yeah, you would if statements. But what would those if statements say?
Like there's a number after the minus sign.
Well, there's a number after this minus sign too. The space doesn't have to be there. Who was in there? I think, yeah, you.
Like the sequence of how the commands are coming through. So we have a
Okay.
command, but the first thing it sees isn't a number, it's a symbol. So we have to assume that since it wasn't a number, that means we're modifying the number after. And there's no arithmetic operation before the minus sign and the 7. So it's looking for 1, so it's going to take that for an arithmetic symbol instead of minus necessarily.
Yeah, that's exactly right. So your classmate said, we know the order, we know the sequence of these symbols. So we know that after a print statement, we have to have a number. So if we see a minus sign after the print statement, we know that that must be a number. It can't be an operator. So that's why the compiler needs to know the syntax of the language, because the syntax defines the correct order of symbols in your language. So if the compiler has this pre-existing knowledge that a statement looks like a print keyword followed by a number, then there's no ambiguity. It can know exactly that this minus sign means we're starting a number and we're starting a negative number. So yeah, very good. Any other questions about, yeah, in the back?
What happens if you want to add a negative number or even subtract a negative number? How does the compiler identify that case?
You want to take a stab at answering? What do you think? So your classmate said something like, whoops, that's still. So you're saying something like this. If I say 4 plus minus 7, in our language, this sequence of symbols means we're adding 4 to -7. Yeah.
So the plus there is a command, and so once you have a command followed by another minus sign, you know that it follows the same I guess grammar that it was functioning before, so it still functions the same way, and you would know that that is a negative number.
Yeah, very good. So what your classmate said is that just like in the case of seeing a preceding minus sign, because we've already seen an operator, we know that this sign cannot be the operator because there can only be a single operator between the two numbers. So by exploiting this structure of the language, our compiler can actually ascribe meaning to these symbols unambiguously. So, but it's the exact same argument. Because we know that there's a certain valid sequence of symbols in our language, we can disambiguate these cases where we have the same symbol being used in multiple ways. So good, yeah. Other questions about this? Yeah.
For test cases for compiler, are you gonna throw us like print -7?
No, I won't give any. You don't have to worry about error handling. You should do enough error handling so that you can handle valid code. We're only going to give you valid code. We'll only give you valid code. Error handling is a pain. You can basically be like a test engineer at Google. They have an entire position for just doing software engineering and test. Yeah.
So for the compiler that we're writing this in C, but we're writing in C, so in C we print out the syntax of LLVM.
So I think, if I can repeat your question to you, we're writing it in C. We're writing the compiler in C, but then we're also processing something that kind of looks like C, right? Is that?
Yeah, I guess.
So this is what makes compiler writing very kind of a mind bender, because usually when you write software, you write a game. What's the input to that game? Well, it's the user interfaces, keyboard, mouse. And the output is some display on the monitor. And so most programs we write are taking some kind of data and outputting some other kind of data. Well, in a compiler, the input to the program, the data is a program itself. So the program is processing other programs. So it becomes very kind of like meta, but it also becomes very confusing when you're processing the language, because you have to keep this distinction between the symbols that you're writing your program in and distinguish that from the symbols of the input program. Yeah.
I've heard a really good analogy for that. It's similar to how the Industrial Revolution was able to occur, in that they were able to build tools for good measurement, and the improvement of the measurement, the ability to make better tools, allowed them to make even better tools. And so with a compiler, you can compile a real crappy compiler program thing, and then use that compiler to make an even better compiler, which then you can use to make your final compiler that works really well.
Yeah, so that's a good point. So this is not tooling to do production. This is tooling to make tooling, which is I think your point. But yeah, that's absolutely right. This is making the tooling that makes other tools. So this is like building a better hammer versus using the hammer to build a house. Yeah. Other questions on this? So we'll get into more of the formal concepts that allow us to mechanically and unambiguously describe these kinds of uses of the symbol for the language, so that your compiler can unambiguously process the language without any of this kind of ambiguity. Another possible source of ambiguity in this language is that keywords and identifiers look really similar. So if an identifier is just could be a list of alphabetic characters, well, we have a print statement. A print statement looks like a list of alphabetic characters. Now, we don't have identifiers yet in Project Zero, so this is going to be an issue in 2 projects when we start having variables. But this is another thing to keep in mind. So just some suggestions when you start programming this compiler, and I really recommend that you literally just dive in and start trying to actually solve this problem, start trying to write your compiler, because I think you'll learn a lot better that way. But just a couple of tips when you go in. One way to architect this compiler is to make a single function for each kind of token or symbol of the language. So make a function that recognizes digits, make a function that recognizes operators, make a function that recognizes semicolon, make a function that recognizes print. That'll help you better organize your code so that you can, when you start writing what a statement is, you can do exactly what your classmate says and exploit the known sequence. So you know that it's got to be a print followed by a digit, followed by an operator, followed by a digit. So if each of those tokens are recognized by a single function, then your compiler is really just calling each of those functions in sequence. Questions about this? Question? No? Okay. So you'll see once you start programming it. I really recommend you dive in and program it. So I've pushed back some of the deadlines because of the closure, but the project zero is due in 2 weeks, a little less than 2 weeks from today. Just to keep that in mind. So just dive in and start coding. And for the next couple of weeks, I will be giving you some of the formal background to be able to more efficiently write this compiler. Okay, so I've given you some boilerplate code. So rather than having to emit LLVM IR from scratch, I've given you this program called template.ll. Has anybody looked at this yet? Anybody look? Okay. This is annoying me. Is it not cutting out? It's cutting out, right? Okay. Okay, maybe that's better. I don't know. All right, so here's this. This is the template. So you don't have to worry too much about what all of this other kind of like text looks like. The main thing you have to be concerned with is this is where we're going to emit or print out all of your LLVM IR instructions. So this is really your main method, and I've given you a print method. And so inside of the project description, it gives you the exact LLVM IR that you're going to be emitting here. So your compiler will just print out this entire block of code from 1 to 14. You just literally just print that out. And that's the kind of header of every program that your compiler is going to write for the first 4 projects. So you just print that out, and then you print out whatever corresponding IR instructions you have here. And then at the end, as a kind of epilogue, you print out the remainder of this file. Make sense? Make sense? Questions on this? So you can just think of this as a template, and you fill in your code here. Yeah?
So is this what you mean when you say we're going to be writing intermediate?
So your compiler so remember, your compiler takes in a source language and spits out another language, spits out other code in another language. So your compiler is going to be, you're literally going to have like a main method in C that just says printf, 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 or maybe, you can put this in a file and read it and print it out. But it's literally just going to like print out this text. Because remember, this file here, even though it looks funny to you if you've never seen LLVM IR, this file is a program. This file itself is a program. So your program, your compiler program, is going to be emitting another program. That's the kind of like mind-warping part of this compiler. There's 3 programs going on here. You have your actual compiler program, you have your input program, and you have your output program. The compiler takes the input program and produces an equivalent output program. So our input program is simple C, and our output program is LLVM. But I recommend just diving in and starting to compile it. I think Project Zero it's not trivial, but I think it's simple enough that you'll get the idea once you start actually trying to build this. Once you start building it, all that kind of like mind-warping part will kind of go away, and you'll just remember, this is my program, this is the input program, this is the output program. Okay, so I've given you this template. Okay, so let's take a look at this LLVM intermediate representation. So it's really not that bad once you look at it. It's kind of like assembly, but it's not quite as bad as writing an assembly. The first iteration of this class, I was actually going to have you write like Intel assembly, but I wanted to learn LLVM IR, so I changed to LLVM IR, and I promise you it's going to be way easier than doing assembly language. Okay, so a couple features of this language is whenever you give a constant, like -43, so conveniently, the constants look just like they do in your source language. So they're literally just the negative sign for the digit 4 and the digit 3. Unlike in assembly where it's converted, well, assembly also does this, but in machine code, it's converted to binary, 2's complement binary for signed integers. But every constant has to be paired with its type. So this is just an aspect of LLVM. LLVM doesn't want to have to figure out what type you mean. So you have to say that this constant is a 32-bit integer, and this means a signed 32-bit integer. So whenever you emit a number, you have to emit its type, which in our language is always going to be I32, and the symbols that represent that number. So I32 is the type, and negative 43 is the number. So we're only going to be using I32 values for compilers. So that should make things much simpler. So variables in LLVM. So remember, this is the target language. This is variables in the target language, not our source language, not our compiler language. Variables in the target language are represented using a percent sign. So percent sign T1 is a variable in the LLVM IR. You might see ampersands, at signs. They represent a global variable, but you don't have to worry about those. You won't be using any global variables, except functions later. And assignments, just like in C, use the equal sign. So to do an addition of two constant values, this is what it looks like. You have to assign it to something, to some temporary value. So give it some name, and I can show you how to automatically generate these names. Give it a variable name, percent sign T1 equals add NSW, the type of the operands, and then the two operands separated by a comma. So practice a little bit with this. I've given you homework to kind of like practice writing this a little bit. But once you figure it out once, your compiler will automatically generate it, and then you don't have to worry about how to program an LLVM IR. Just like in assembly. You write the compiler once, and you don't have to be an assembly expert. So this NSW, just put that there. Don't worry about it. It's for LLVM to handle undefined behavior, like for overflows or underflows. And we can just generate these variable names using a counter. So you just have a counter for give me a new variable name, and you can just always say percent sign T and increment that counter. The reason for this is that LLVM uses SSA, or static single assignment form. We'll see this a little bit later in the class when we talk about optimization, but all it really means is that variables can only be assigned once in LLVM IR. And there's a specific reason for this that makes optimization in C easier. But just be aware, for all of your temporary values, for when you're computing these arithmetic operations, you have to create a new variable name. So if you get an error when you're trying to compile the LLVM IR, we're trying to actually run that program, and it says, can't use this variable twice. You have to just generate new temporary variable names. Questions on this? Yeah.
How far can we go? Can it be any letter and number, or is it like mixes where you only have like 8 of those?
Oh no. So this is what's great about LLVM IR is that it's kind of an idealized assembly where you have unlimited registers. So you can think of these as registers, kind of, and you have an unlimited number of them. So just like in C.
A1 and go all the way to 8,000, and then just go.
Yeah. However many, the size of the identifier that LLVM supports. You shouldn't. I'm not going to give you large programs, so you're not going to run out of temporary variables. Why would we need? Oh, good question. Yeah.
With the things like the tempo, would it be just a single letter, or could we actually do like percent and write the whole word temporary, and that would be fine?
Well, you can only assign them once. So if you need multiple temporaries in your program, which you're going to need, the reason I recommend using T and then a number is that you can just generate them easily by just incrementing a counter.
Okay, but it's not but that's just the ease of use. It's not that it can only have one letter and then a number.
That's right. Yeah, it can be any arbitrary. Now, if you have percent sign and just a number by itself, that has some special meaning in LLVM, which we won't get into. But so why would we need temporary variables? Why do we need to generate these temporary variables? So our input language doesn't have variables for Project Zero. It's just doing arithmetic computation. So why would we need to even have these temporary variables? Yeah, it's storing in registers. Yeah, exactly. It's storing It's storing register values. So if you were to write assembly and you wanted to do some computation, you have to store the result somewhere. You have to store it in a register. So you can think of these percent sign variables in LLVM as like an unlimited set of registers that you can name anything you want. But just like in assembly, you have to explicitly say what machine instruction you're using. So in C, you can do arbitrary math expressions with parentheses and all kinds of order of operations. But in LLVM, just like in machine code, you have to do one operation at a time. And that's one of the things that compilers give you for free. That's, it's kind of invisible to us now because we're so used to writing math expressions. But remember that the hardware doesn't know anything about math expressions or order of operations. It just knows individual arithmetic operations. Okay, so yeah, as I mentioned, NSW, don't worry about that. Just treat add NSW as your addition operation. And also note that for later projects, the operands don't have to be a constant value. They can also be another variable. So this can be like percent sign T1, for instance, or percent sign whatever, percent sign temporary. So the operands to, just like in assembly, the operands to an addition can be another register instead of a constant. So there are other instructions like subtraction, multiplication, division, and remainder, which you're going to implement all of these. Yeah.
With the expression at the top, is that just saying add to? Is that just 2 plus 3?
That's just 2 plus 3.
Okay.
That's it.
So the structure is we're saying we're going to add. It's going to be an I32, and it's going to be 2, and 3 is going to be the thing that we're adding. That's the general structure of the
That's right. Yeah, that's exactly right. So these are the two operands, 2 and 3. They are 32-bit numbers, and we want to add them together and store them in this register at the end. Yeah.
In basic arithmetic, and probably even with like multiplication and division, does the I32 or the type identifier, does that identify both of the operands?
Yes. Yeah. Does this type identify both operands? Yes, it does. You don't have to write it for the second one. Yeah.
Okay, so that you can't. Is there a way to add different types, or do you have to convert?
You have to convert. So LLVM it's kind of like a typed assembly where it's not going to allow you to. So in assembly, you could just sort of mess up and do type errors where you add what you thought was a 32-bit number to a 64-bit number. And even Intel has different instructions depending on which bit width you want. So this is why we have this type here, and it only allows the operands to be the same type. So there are other instructions in LLVM that allow you to sign extend or either sign extend or zero extend the 32-bit 64 or short to long, whatever you want to do. But we're not going to have to worry about that. So there's only one number type in our language, and that's 32-bit number. Just to make it simple. But there are that's a good question. You can do this with LLVM. Okay, other questions? Other questions on this? Oh yeah.
So the division, the members, they don't need the NSW, or?
Yes, that's right. That's right. Division does not need it because you can always have it divided by 0. This stuff is really just for LLVM when it's doing optimization to know about undefined behavior. So in C, you can have an overflow if you add two numbers. If you add 2 to the 32 plus, or 2 to the 31 plus, 2 to the 31, you're going to get an overflow. It's going to loop around. If you divide by 0, you're going to get an error. And so LLVM has a sophisticated way to kind of track this in its when it's doing optimization. And same for S remainder. Remainder is just like division. You can have a divide by 0. Any other questions on this? Yeah.
So the ordering is at 2 plus 3, so it's
Would be, yes. Yeah, the ordering matters. So the first operand is so if this were subtraction, it would be 2 minus 3. Okay, so printing. We're going to use printf, but as we saw, I think in the last lecture, the one I posted online, printf is a function that somebody else wrote for you. And when you compile and link your program, The compiler and the linker and the operating system is figuring out where printf, the code for printf, is for you automatically. So if you didn't have that linker and loader, when you call printf, there'd be no function there. You'd have to write it yourself, what printf is. So we're going to be doing the same thing. We're going to be writing an LLVM program that calls printf, but the linker is going to make sure that printf is there. And I've created this helper function for you called print_integer, which you can just use to implement those print statements. Let's see, did I give? Oh yeah, I'll show an example of this. So this is how you call the function. So you're going to have to emit this whenever, for your print statement. So you just say call the type of the function. So in this case, the function is just a void function, @ because it's a global value, print integer, and then the variable here with its type. So just like the other operations, we have to tell explicitly LLVM what type of value we're using. But this is basically just like a template. So whatever temporary variable you use here, just fill that in using a printf format string. Questions on this? And also, I think one thing to keep in mind is I think you cannot put a constant here. Am I right about this? Anyway, I actually can't remember, but I'll show you an example of what one of your compiled programs will look like. Oh, so by the way, here I am in the just before I get into this. So here I am inside of my syllabus. So everyone should either git clone or download the syllabus. Can everyone see this? Can anyone not see this? Can anyone not read this? Maybe I'll make it a little bigger. So I've downloaded the syllabus, or I've cloned my syllabus. And in the projects directory is this Vagrant file. So if you're using Vagrant, you just run Vagrant up and then Vagrant SSH from the projects directory. And this will take me into the virtual machine. So just notice here that my command line prompt looks a little different because I'm the Vagrant user on a different machine. And also conveniently, if we go to the Vagrant directory /Vagrant, so this is in the root of our file system. So ls/ this is the root of our file system. Take operating systems and learn more about this. And in the Vagrant directory, this is actually mapped to wherever we ran Vagrant from. So we ran Vagrant from the projects directory. So now the Vagrant directory inside of the virtual machine is mapped to the syllabus directory. So just to show a little diagram of that. So when you run Vagrant SSH, that gives you a bash shell inside of the virtual machine. So here's your host. Here's your virtual machine. When you run Vagrant SSH, that brings you into the virtual machine, and it automatically maps your projects directory into the /Vagrant directory. So whatever you do here on your host machine, if you clone your project repository or you put homework2.ll here, that will be accessible in your virtual machine under /Vagrant. Yeah. No, I think it should be mapped. Yeah, it should be mapped as long as the virtual machine is running. It should be mapped. So yeah, so you can edit in Windows or Mac or wherever you're comfortable, and then compile and run inside of the virtual machine. Okay, so I'm here inside the projects directory, which is mapped to Vagrant inside of the virtual machine. And so inside of examples, I've given a number of different examples of LLVM code. So this all program is one of the test cases that I've given you. Actually, right now it's one of the only test cases. So one of the test cases I've given you in Simple C. So this is what the test case looks like. It's just a print of every operation that we have in our language. So we've got plus, minus, etc., and the other type of statement where we just print a constant. So what your compiler will output is an equivalent LLVM IR program that looks like the one on the right. And all of this code here, this is just our template.ll. This is just our boilerplate code. So you just spit that out with your compiler, And here is where you emit your own code. So on the right, we have the equivalent LLVM code to our simple C program. So notice the first line is setting a temporary variable to the addition of 2 and 3. And then we call our print integer function on that temporary variable that we created. And these 2 lines, that's pretty much all your compiler will ever need to output. It just needs to do that for this kind of statement where we do an arithmetic operation. So even without any of this fancy compiler formalisms and syntax and grammar, I'm sure most of you can sit down and hack together something that takes in these statements and prints out these statements just through sheer brute force and ingenuity. I'm sure you're all capable of that. And I want you to do that, actually. You don't have to follow the formalisms to do it. But once we get to more complex language constructs, hacking it together is going to be very, very painful. So so you can just process these kinds of statements and produce these kinds of statements. So some caveats when you're trying to hack this together, if you look closely at the lexical specification, you can have any amount of white space you want, or even no white space between certain tokens. So if you were to hack, if you had a very expedient hack, you might actually recognize the new lines and the spacing and everything. But our language is more flexible than that. These, for instance, the equivalent program could really look like this. Actually, no, it could look like this. So that's equivalent to what I had before. But anyway, yeah. So I'm sure all of you could sit down and hack this together just over a weekend to produce this kind of code. Okay, so our printing a constant just looks like calling the print integer with just a constant. So yeah, I was confused. You can put constants inside of the function call. I don't know why I thought that. Questions on this? In the back, yeah. Did I hard code the one on the right? Yes, I hard coded it. I did not do the project. I didn't do the project. I wrote enough compilers for my lifetime. I just hard coded this. Any other questions? Yeah.
So when we create a program, are we supposed to say that simple, file extension is that simple C?
Oh, good question. So the dot simple C. So remember, your compiler is a program, and it's a special kind of program because its input is another kind of program in the source language, and its output is yet another program that's equivalent to the input, but in the target language. So the input programs for our compiler are .simple C programs, and they look like this. The output are .ll programs, which are LLVM IR programs, and they look like this. So this is, I really recommend just sitting down and coding, and you'll get it. You'll get it if you just sit down and code it. All this mind warpy part of this whole Inception, Matrix, virtual world stuff. This will all subside and it'll make sense. It'll make sense. You'll be able to distinguish the program the compiler program from the input and the output. But you literally just hack together something that takes this kind of code and produces this kind of code. Questions on this? Any other questions on this? Yeah. So the question was, our whole goal is to make a program that takes the left one and turns it into the right one. So to be pedantic, no, because I also want you to be able to take, this program, and I want you to be able to take this program, and any number of different programs that have some kind of similar shape. So this is the whole point of the compiler formalisms that we're going to learn. Is that what do you mean when you say programs of the kind on the left? What is the precise mechanical description of that? And this actually starts tying into human language and linguistics. What does it mean for us to understand language? What is language? And how do we process it without any kind of mystical language existing out there? How do our brains actually process these language? And some of the techniques that we're going to use actually come from linguistics and computational linguistics for specifying these grammars formally. So it's what's a little tricky for humans is that we all have this incredible language capacity. So all of you can just look at this thing on the left And like without even thinking, you're just automatically parsing this, and you know it. Even with a little bit of C background, you already know what this means. You can already guess what this means. But a computer just sees individual characters, or at least, actually, it doesn't even see that. That's anthropomorphizing it. It doesn't see anything. We can write a simple program that reads characters one at a time, but we have to write an algorithm that can actually ascribe meaning to those symbols in the way that humans do, virtually automatically. So yeah, in short, you want to take programs on the left and turn them into programs on the right. Okay, any other yeah.
What kind of software or program are you using to do this? Like
the compiler. You're writing the compiler that does this. This is your project. This is project 0. This is what you're writing it. You're writing it. You are writing this technology. Yeah.
So we're making we're using make to, or we're using Clang.
You're using C. You're writing a program in C.
But we're building the compiler, and then we're passing the built compiler that file, or a file that is similar to that.
Yes, you're writing a program. You write that program. That program is going to be called Simple C if you use my make file. You're writing C. You write that program. It's going to be called Simple C, and then you take. So this is the specification of the. Let's see, where is this? So you run a program. You write a program. It'll be called Simple C. And it should be able to be run exactly like this, where you pass in the name of the program as the first argument, and its standard output is the LLVM IR. So this little caret here, or this little greater than sign, if you haven't seen it, just means take the standard output and redirect it to a file. So whenever you do printf, if you're not doing fprintf, you're just doing printf, by default it goes to standard output, goes to the console if you're running it interactively. Yeah.
So when you say you've already created Simple C, of course, we should fill it in, like what you want to do?
No, I haven't given you any template. So I gave templates last semester, got some complaints. They were pretty hairy, they were pretty in-depth. So this semester, it's all from scratch. You're writing it all from scratch. But the compiler is much, much simpler. So you have the freedom to, architect it and design it how you like, and the experience of, writing C from scratch. But it's, it's fairly straightforward, Yeah.
So your C program can just take that file as input with that extension and it'll be okay? Like that extension can be anything?
It could be anything. The extension could be anything. The extensions are, again, they're just a convention. Yeah. It would print to the screen, yeah. If you just do printf, by default it prints to the screen when you're running it interactively. Yeah, that's right. Yeah. So this is like OS stuff, Unix stuff. I think it's good to have some experience with that. It gives you some good OS experience. Other questions? So to see, I guess, kind of see what it looked like. So I don't have a working program here, but you're going to run make. And whatever your main function looks like, you're going to get this Simple C program. And when you run Simple C, you should be able to take the test program all.simplec and produce all.ll, produce that file that it should probably look exactly like that all.ll file. It's maybe modulo some spacing. But that's roughly what, that's what the output will look like. And then once you have that LL file, so I have an example here. This is my LLVM file that I just showed you. You can compile it with the same kind of syntax that you use for GCC. So Clang is more or less drop-in replacement for GCC. The difference is in the internals, it uses the LLVM intermediate representation internally. If you've who's heard of like Apple's Swift language? You guys heard of Swift? So Swift was built on LLVM IR. So LLVM is an industry standard compiler framework for writing industry standard compilers. And there's lots of languages that use it. So Clang is the C front end for LLVM. So that's how I build my LLVM file. So what's confusing about this is that you're using Clang to compile your compiler program, and that program is outputting LLVM IR, and then you have to compile that to machine code. So I was hoping that was clear in the last lecture, but there's a lot of compilation going on. Maybe I should draw a diagram. I'll draw a diagram next time. Or actually, I'll just draw a diagram now, just to make this a little clearer. So the program you're writing, is simple C. So that's you. You write that, okay? That's you, the student. You also want to write your own test cases, but we're going to give you test cases. That is going to be input to Simple C, your Simple C compiler. The output is going to be some LL file. Now, because that is the LLVM intermediate representation, it's an abstraction, it's an abstract assembly language, that will be passed to Clang, which you did not write, to produce a program, to produce an executable program. Then this gets passed to the loader and to the OS to actually run. And then you get the output of that program. So it's a little bit of a Rube Goldberg contraption here. But internally, this is really what real world compilers do. They have a front end that processes the source language and turns it into the intermediate representation. Yeah.
Could you go back to the initiative that so you have the print to 2 + 3, and then on the other side was.
Oh yeah.
So just so that I'm making sure I understand, it's like, let's say that we have we're going to have a file that has things like that written on it, right?
Say again?
Are we going to have a file that says print 2 + 3 and all that?
Yeah, but you should be able to write them
and then
yourself.
what's going to happen is we're going to write a C program that takes it character by character. It's like ICP, ICR, ICI, ICN, ICC. Okay,
Yep.
now I'm going, and then over on the other side it says, okay, we're going to write a function line that is the call void at print, and then keep scanning it to figure out how many numbers and if we're going to do an add or a subtract or whatever, right?
Yeah. So you're going to read these in one character at a time.
And
Recognize this as an entire statement, and then print out a corresponding equivalent statement.
So
for
we're
it.
literally building the main over there as we're scanning all the characters on the left.
Yeah, you can do it like that. You can do it as you go along. I mean, if you just read in a P, there's nothing to print out for LLVM, right? You don't know yet what this is. You just see a P. Once you say print 2, you don't necessarily know yet that this is going to be an addition. So you're going to have to do a little buffering. So maybe I should start on the next lecture, actually, because we have a little time. This will get into what this process is, and it's called Lexing. But yeah, go ahead.
After we use Clang on the LL file, will there be an executable?
Yeah.
We can.
Yeah, it'll produce an executable. So when I run. Let's go back to examples. So when I ran this statement here, this, just like in GCC, produces the executable called all. So when I run that, I didn't actually run it yet. So when I actually run all, that's the output. Sorry, I didn't actually run it. I think was there somebody? Yeah.
Do we need to catch syntax errors?
No, don't worry about syntax errors. Assume the input is correct. You can assume the input is correct. You should do a little error checking of some kind, but you can assume it's correct. That makes it very complicated. Yeah, there might be some cases where I want you to do a little error checking for type checking, but syntax errors, you can assume they're correct. Yeah.
So would it be alright if our compiler accepts type input so we can put this in the terminals?
No, it cannot accept piped input. It has to be the way I described it, because for grading, I want it uniform for grading. But it shouldn't matter. I mean, it's equivalent. It's just scanf versus still scanf. It's the same functions you use. So standard in versus a file is identical C code. Okay, let me, oh yeah, go ahead.
What's going to be doing with semicolons in this assignment?
Say again?
With semicolons in this assignment?
What about semicolons?
Will we be using them in the expression?
Well, yeah, if you look at the input file, at the end of statements is, oh, parentheses, no parentheses. So it's only statements of this form. So let me go into more of the like the formal stuff so that we can actually have a way to describe mechanically what this language definition is. Because questions like that, it's like, do you have spacing? Are there parentheses? What is the actual like structure of the language? In order to do that in a mechanical, unambiguous way, we need some formal math to do that. So did I? Yeah, this lecture is finished. So let me get a little bit started on the next lecture, because I think this will help you start doing the project. Let's see how much time I got. Okay, 9 minutes. So we'll just go into it very, very quickly. So the first thing that the compiler needs to do is it needs to take this stream of characters, just like your classmate said, it just sees P and then R and then I, and it needs to interpret these as groups of characters so that it can know what are the symbols of the language. So the individual characters are not the symbols of C, they're the tokens of the language, the identifiers and the plus signs and the parentheses and the keywords. So this process is called lexing. And the reason it's necessary is because source files are text files. They're not. There's no the numbers that make up that file. The binary code for that file doesn't mean that they are actual like integers or numbers. They're really just streams of characters. And so we as humans, one thing that's so deceiving about this problem is that we as humans can very easily lex or group characters into words. So when you look at this, does anybody see anything here? What does this mean, this first one? Does anybody make sense of this first one? Okay, good. So it's like a Rorschach test, I guess. So this second one, does anybody see the groups of words here? I mean, it's obvious, right? Hello world. But what about this third one? Can anyone read this? Everyone can read this, right? Because your mind is automatically grouping these words together. A computer cannot do that unless we write an algorithm that describes what that means. And so just a quick refresher on C. Characters are, they're bytes. You use the char type. They have to be in single quotes. Hopefully this is a review. You can only put a single character within the single quotes. So what about /n? Why is it that we can put what looks like two characters in here? Does anybody know?
/n is treated as a single character.
/n is a new line. It's a single character. It's a new line character. We'll look at that in a little bit. But whenever you're like using character type, they have to be in single quotes in C. Has anyone used characters before? You guys done string processing? I think everybody should have done this, right? String processing. And so as I said before, if you want to read a single character at a time from a file, you use this fgetC function. Yes?
Are we going to have a new line character in our .ll file?
In the .ll file?
Yep.
You don't have to, but yeah. You can. Yeah, it's easier. I mean, it'll be easier to read the output file. But yeah, you'll have them in there. So conceptually, what the lexer does is it takes each character from this input. So even though we see spaces here, these are actually characters in the input. New lines and spaces are characters. So it reads these one at a time and groups them into groups of sequences of characters, and it names each of these groups according to the lexical specification. So all it's saying is when I see two digits next to each other, the lexer says, aha, I know that group of characters is a number. When I see a negative sign followed by a digit, I know that that's a number. When I see an asterisk by itself, I know that that's the time symbol. So one of the very first things you'll probably want to do when you write this compiler is write some code, which is called the lexer, and you can even put it in a function called lex, that is able to take these characters, read them one at a time, and buffer them, read them into a buffer, and whenever you see a complete word from your language, name it, call it a print, and I can show you how to, and we don't have enough time today to go into the details of printing, but I'll show you how you can name it. You can just give a number to each one of them. You can just give a number to each of the tokens. So the lexer takes in a stream of characters and it produces a stream of these tokens. So one way to write your compiler is to literally say lex file and have it produce an array of tokens. So a little terminology, the actual group of characters that you recognize, that the lexer recognizes, is called the lexeme. And the name of the symbol, the kind of abstract symbol that represents this group of characters, is called the token. Certain tokens can have token attributes. So for instance, a number, its attribute is the value of its token. So this value is, it seems a little redundant, but its value is -2. But if you were writing a compiler to machine code, you may have to represent that in binary, for instance. In LLVM, it's convenient because we also represent it as text. So other tokens like the print statement, they have a single lexeme. So there's no attribute we need for this. There's only a single possible lexeme. The attribute is a way to identify different types of lexemes for a single token. So these are some examples of some common tokens from other languages. The if keyword is just the characters I and F. It only has a single lexeme, that's IF. IDs in most language, identifiers is a letter in most languages followed by letters and digits. Some examples of these are P followed by I, SCOR, etc. So these are the lexemes and these are the tokens. So there are many potential lexemes for a single token, depending on what the description of that token is. So these are tokens with their potential attributes. So if I have an ID, its attribute might be a pointer to the string in a table. Okay, I think this is the last thing I can cover. But so the reason that we have to do this is because characters are actually represented with numbers in the machine. So I don't have too much time to get into this, so I will just show you a quick example of what this looks like. Uh-oh. Here we go. Let's go back here. Sorry. Okay, so I use this little program called a hex editor or hex dump. So if I take my hello world.c program and put it through this hex dump, you can see all of the characters here on the right. So it all kind of runs together because the new line is actually a character. New line is not space. The space is represented by an actual character. And each one of these characters is represented by a number. So hex 23 is the hash character. Hex 0A is the new line character. So I'll go into this more next time since we only have a minute. But this is what the machine how it actually gets stored, how these text files actually get stored on machine. And I'll talk more about this code next time. Hello.